And Denisha, I did get you guys.
Thank you.
So, what you gonna do about your phone? All right, so ready?
Yeah. Are y'all ready?
So you going to the funeral?
Are we first? Are we
How you do? So you going to the funeral?
Yes.
And look up some old black person that from your character. And just be like, this is my aunt, this is my auntie. Like y'all have the same last name. Well, you don't know the black culture that black people have called everybody auntie. So this is a very close family friend. You win every time. All right, so welcome back. Congratulations once again. Almost there, at least for this particular semester. So we have our second group of students who will be presenting their final presentations for senior design. Thank you, Dr. Nicely, for joining us today. And don't forget, you got 10 minutes.
Okay, so I'm Tanisha. My name is Malik.
My name is Francisco.
And we're PBG. So our topic is chorionic villus sampling. So chorionic villus sampling is a procedure that is done between 11 and 14 weeks to detect chromosome abnormalities and genetic disorder like spina bifida Down syndrome. Jan Moore was the first to attempt and describe CVS procedure in 1968, which was the transcervical technique, but it was rejected. And by 1982, researchers at the University College Hospital of London improved the method, and by 1984, the transabdominal technique was introduced. We're going to focus on the cervical technique. So this is the chicken breast model that doctors use to practice on before performing the procedure on patients. Like you can see in the first picture, they just cut the chicken breast open. The second picture is they use a condom and put like water in it. So that's like a mimic of the sac that the baby's in. The third picture is the placenta, which they use for tofu. Then they like stitch it up, and that's the completed model at the bottom. They go in with at the bottom with a catheter and like a needle probe, and they go in and take genetic villi from the tofu, and they test that. So those are all the materials that they use. So our problem statement is the increase of risk during chorionic villus sampling has been observed to directly correlate with the experience and skill set of the doctors performing the procedure. So our need statement, there are limited resources for doctors to practice the CVS procedure before performing it on patients, as their current method involves the use of models that cannot accurately stimulate the varying physical anatomies of patients, nor can they be reused. So there is a need for better models so that doctors can stay continuously proficient at the technique.
So our customer needs and stakeholders. So the first activities that we performed basically was researching for the chronic villus sampling. We mainly focused within the miscarriage rates of the CVS model. We actually contacted the Greensboro Imaging connected with the ultrasound techs. We actually interviewed Dr. Goodnight from UNC Chapel Hill, and we also participated within the construction of a chicken breast CVS model that he actually let us work on. From the slides before, that's what it was. Our planned activities would be contacting the OBGYN for departments of home health, interview any doctors about the CVS potential needs, and also contact the manufacturers within the training models of the FDA regulations, known as the 3B Scientific, WorldPoint, and Blue Fam.
So the disease state analysis for CVS is a little interesting because it's just an invasive diagnostic test. It's not actually curing or trying to fix anything. So our main focus areas in the anatomy and physiology portions are the cervix and the chorionic villus, or the chorionic villi, which is basically what are being suctioned out. The pathophysiology is just basically the sampling needle and the catheter sinking through the cervix and reaching the placenta. The patients that are, the clinical presentation of this test is basically mainly focused on pregnant women who have tested positive for any type of genetic abnormalities or who also have a history of genetic abnormalities within their family, and also patients who are over the age of 35. So those are kind of our main focus. And of course, you also have the doctors and med students who also practice with this as well. Epidemiology includes any possible genetic disparities that can be found within the fetus. Because like I said, it's just a diagnostic test, so they're not really sure if there's anything wrong as of yet. And the economic impact, we realize that the cost of CVS, depending on if you have insurance, can cost between $1,300 and $4,800. So it just depends on your insurance company.
So our market segment analysis, so the total available market is that we have 8 million pregnant women each year. So that would give us a total of 141 MP programs within the US. Our served available market, so we saw that 3 million genetic fetal defects happens just about every year. Approximately, we would have 32,624 OBGYN within the US. Our target market would be with women with family who have history of genetic disparities. So this will also target medical school with OBGYN programs.
So some regulations that we're kind of researching about. So because we're trying to make a CVS model, we noticed that it's probably going to be with the uterine surgery trainers and simulation models. However, the main problem that we're realizing that keep occurring is kind of trying to reduce reverse research on it. So even though we kind of know what we're looking for, but it's kind of hard to find the regulation number. So we know that it's under 21 CFR 800.61, which are basically assisted reproduction devices. However, actually trying to find actual regulations for these devices are still in the works. But so what we did do is we took other medical devices such as CPR assisted devices, like the models, and we used their regulations such as basic regulations such as labeling, registration, medical adverse events, and also the manufacturer mechanical testing as well. So we figured that our model also would have to follow within those same guidelines as well. Believe it or not, the IP search for these were actually a lot easier than the FDA regulations because models are cleared a lot. So you have your surgical simulation models. You also have your pelvic model, postpartum uterus models. So we were kind of using those as research for the FDA regulations. And we also, because we realized that we would need continuous usage, we also looked up fibrin monomer sealants, which basically, whenever you puncture, it'll basically seal itself back up. So we were thinking about using that for our model in case, say, a medical student actually perforates the condom. So you don't have to keep taking it out and redoing it.
So our criteria for this is that it cannot be hard for doctors or the medical students to reconstruct. This material must be composed of affordable. They also should have a similar ultrasound imaging. That way it can compare with the actual patient. So our constraints would be it has to be similar to the physical anatomy of the uterus in order to mimic the CVS model procedure. They should appear within the ultrasound with a frequency of 1.6 to 10 megahertz. Because if that doesn't happen, you won't be able to see anything. It'll be pitch dark black. You must be able to withstand at least 5 multiple attempts. So after the 5th attempt, you throw it away and bring back the new CVS model. It must also have a variation of realistic approach. That way, the person who's training on it will be much more comfortable when the real thing happens. And the angles of the uterus, layers, skin, cleaners, and also the ultrasound imaging all deal with that.
Questions, comments, or suggestions? Okay, all right. I'll get started. Thank you for the presentation and for your work up to this point. And kind of what you've researched thus far, what are some potential ethical concerns that you would have in trying to come up with a solution for this kind of problem?
Well, so there are actually other models out there besides the chicken breast model. So if I should probably ask if you're referring to the model itself. There's another model that is a fetus that actually involves a pig fetus that is actually kind of constantly being used versus the chicken breast model. And of course, it's kind of costly, and then you have people who don't touch pork and things of that nature. And then the same, I guess, can be said for the chicken breast model as well, but not as much as a pig fetus. So I haven't really seen anything that had any ethical issues with the chicken breast model. Now, if you're referring to the CVS procedure itself, that's where it gets kind of interesting, because a lot of people feel like, well, you really shouldn't check to see if there's something going to be wrong with your baby so you can abort it eventually. Because some people, they see that as you're just looking for a way to abort it, or if it's not perfect, you're going to abort the baby. But in some cases, it's just not true. A lot of the times when people get this procedure, according to Dr. Goodnight, it's already at a high risk for abortion or complication anyway. They're just checking to make sure. So I think the South isn't really known for doing this procedure. They can do it, but the North is more known for it. So that's the main one.
And so I guess in terms of where you are right now, what would you say is your central problem that you're trying to address? Is it more of a modeling situation, or is it?
It's definitely the
It's
model.
definitely the model.
Because as Nick mentioned in the problem statement, the higher the risk is mainly because of a doctor or medical student who couldn't practice or didn't practice enough. So that's where the modeling situation comes into play, because they said they've actually tried on real life patients, but unfortunately most patients are abortion patients, and they said emotionally speaking that's not the best time to practice on someone. So that's what we're focusing on.
And then, so as you're kind of looking at your criteria and your constraints, so if you look at your criteria, how are you going to test? You can if you want to, if you need a reference, but I'm just saying, in terms of the bullet points you presented as your criteria, how are you going to test your outcomes against those to determine what's successful and what's not?
So
Can I be hard for the doctors to reconstruct? So I guess that just comes back from like the materials that we'll be using for the model. Like speaking, like again, like she was saying, like speaking with Dr. Goodnight, like on Monday, we want to not make it, because like the chicken breast model they have now is a good model, but they don't get uses out of it. So we want to make it so kind of like replicate the model, but make it so more efficient for them. So our criteria, but
Just, yeah. Let's do that so we can look.
right.
So like composed of affordable materials that are affordable and they cannot be hard for the doctor or medical students to reconstruct. So they make this model. So we don't want to make it too complicated for them. We want to make it simple as possible, but make it also so it can replicate like a pregnant woman. If that makes sense.
So how, I'm sorry.
Also, when it comes to composing the materials that are affordable, most oftentimes people would just say, oh, well, use silicone and go from there. So the problem with silicone is, depending on how we go about the model, it can be very expensive. And to have to keep remolding and making sure we have a good attempt, we're not still sure if it's worth it to just say silicone just yet. Because I'm sure a lot of training models, the really expensive one use silicones. Silicone and some other type of self-sealing apparatus as well.
You have to be aware, because they have to be a material that can, like an ultrasound can read, or that ultrasound can go through. So it can't be plastic or can't be like a hard material. The ultrasound has to be able to read to go through the inside.
And it's like you have to do that, and then you have to make sure it's self-sealing because they're going to keep piercing it.
Yeah.
And then you have to make sure the insides can be changed, and then you have to make sure that, like you said, the ultrasound works. So right now, it's like they have a good model, it's just you can't reuse it. So we were thinking if we could take what they have and make it so that it can be reusable, and that you don't have to throw it away after every use.
So if you could go to the next slide real quick, because I think one of the things that we're going to need to do is refine your needs and your problem statements. So it's a lot more targeted, but also you have your criteria and some of your constraints mixed up. Okay. So again, as we talked about, constraints are like limitations that you need, and you want to be very specific about them. And criteria should be the performance base. So what do you want it to do, and at what level, right? So if you're saying, for example, you want it to be self-sealing, then that's like an action. That's something you want it to do. So that would be a criteria per se, right? And then if we go back real quick and we look at the criteria, it's going to be, how are you going to test that something is hard for doctors and medical students to reconstruct, right? Is that
You told us that we can bring it back there, like, we can test it.
right? You can test it, but I'm saying what's going to be the metric that you put
Okay.
that up
So that would be
against?
constraint. You're saying that would be constraint?
Well, no, you can write it as a criteria, but you need to be specific.
More
Right.
specific about
So is it going to be, we're going to do surveys and Likert scales, and if we get 80% of them that are rated as super easy, then we're good. You know, but to put these highly kind of subjective things up, that's not concrete enough criteria, okay, especially at this stage. What is affordable? What are you gonna say is affordable? Because that, yeah, so like we said, we need like specific numbers, because what's affordable for your simulation is probably different from what's affordable for the self-intubating tube simulation,
Gotcha.
right? And then, again, give us some numbers, a similar ultrasound image, you know, what does that mean? And I think you actually were a little bit closer in the criteria, in the constraints, because you said it has to be within a certain wavelength or be visible within a certain wavelength of the ultrasound machine, right? So that's something we can test against, right? With these, we can't really test against. It's all subjective, and we need some engineering numbers to prove it, all right?
So if you don't mind me asking, in the case of the criteria where you have your third one, you're saying must have a similar ultrasound image in comparison to an actual patient. Like what numerical, what data are you looking for in that?
So then you need to look up ultrasound and what those, or go back to your imaging books, because you have grade, you know, there's all kinds of grade levels, field of view, there's all kinds of things. I mean, you have to tell me kind of how are you evaluating ultrasound on the actual patient, or what you mean by that.
Okay, so I guess what I'm asking is, so looking at our constraints, because our constraint was you have to do it between a frequency of so many hertz. Well, I guess are you saying put that in the criteria as well and then make the constraint something else?
Yeah.
Okay.
And this still needs to be more specific.
Okay.
But in the sense of like having it simple.
Yeah.
So think about, so I think what this also means is you may need to dig a little bit more into the background about what this stuff means. So how do we look at ultrasound? How do we process these images? And if I'm saying that the needle or the model needs to be the same as a natural human, along what lines? Is it grayscale? Is it,
Gotcha.
what does all that mean?
You know what I'm asking? So say I were to take an ultrasound, right? And because he actually showed us like what would be the baby, what would be the placenta, and all that. So if you were to show like do a comparison and show that this is where the placenta is, this is like what we expect our model to look like. Is that more specific? Like
I would say use the actual scale of the ultrasound. So when you do an ultrasound, it has a scale. You can say, okay, from here to here is where we know the fetus should be, and from here to here is like that. So you can use the scale that's on the image. It's either like in centimeters or like millimeters.
Okay, thank you.
Yeah, so stuff like that. Okay, we can talk more about it offline.
Yeah.
Thanks. Next, good job.
Well, we're gonna run out of time for this.
Yep, I looked at the clock and said, yeah, we're definitely going.
Read that note card. Come on.
Yeah. Everybody else at like 12, 13 slides. Is that like 12?
No, don't do 15.
We do?
We have 15 with actually.
Okay, coordinate.
I'm Courtney Wallace,
I'm Sarah Bolts.
I'm Joshua Keku.
and our project is the ECMO machine, and we're trying to innovate the cannula diameter of extracorporeal membrane oxygenation to support premature heart and lung function of neonates. And our team name is L for N, which stands for Life for Neonates.
So some background on our actual project. We're doing our project on the ECMO for preterm babies, and every year 15 million babies are born preterm, which is before 37 weeks. And around 184 countries, there are 5 to 18% rate of preterm birth. And so why is preterm birth so dangerous? because babies are born with inadequate organs because they're out of the mother's womb so early that they weren't able to start creating those organs. So they're not able to they have instability in their temperature, a lot of cardiovascular problems, respiratory problems, and more due to their organs not being able to function correctly. So therefore, doctors will put these babies on ECMO, which is a life support machine, and it is utilized only on the it's a life or death type case. So it's utilized when the babies are at a brink to where if they're not on this machine, then they might die. And then to give you some perspective, so premature birth has different levels. So you have a late preterm, which is around 34 to 35 weeks, which isn't as severe. You have moderately preterm, which is around 32 to 34 weeks. And then you have very preterm, and then you have extreme preterm. And we're focusing on between moderately to late preterm because that's what we've seen is the most relevant for our cases. And on average, the babies weigh between 4 to 5 pounds and are between 18 and 20 inches.
So this is just a little bit more background on what ECMO is. So like Tara said, it helps support the heart and lung function so they can heal properly, but it also pumps the blood to circulate through the lungs to get the oxygenated blood back into the bloodstream. And in the image, you can see where the actual cannula, what we will be focusing on, is placed into the neonate and how it's in a circulatory pump for the oxygenated blood to go back into the bloodstream. So our problem statement is that the smallest cannula tube, the diameter is too big for the smallest size ECMO machine to support the heart and lung functions of the premature babies who are less than 34 weeks gestation. This causes the risk to outweigh the benefits of the ECMO machine. So our need is that there is a need to support heart and lung function of infants that are less than 34 weeks gestation because of the size of the smallest the smallest cannula tube of the ECMO machine.
So this is the cannula tube, or one type of cannula tube by a certain company, just so you can see what it looks like. And the cannula tube the whole ECMO machine is dependent upon the circulation of the blood from the circuit to the patient. So the cannula tube is very important, and having the right size and shape is important in order to keep the blood from being turbulent or blood being damaged, and for proper blood flow. So this cannula is the interface between the circuit and the patient, and optimal cannula will maximize flow and minimize any damage towards blood. And every cannula is different, and it's chosen based on the size of the patient and the way their blood is flowing. Okay, so for our stakeholders, we have doctors and surgeons because they will be utilizing the actual product, and that's who we would most likely pitch our products to. Parents, because neonates are unable to make decisions for themselves, so getting a parent's perspective is the next best thing. And then we have the Extracorporeal Life Support Organization, also called ELSO, which they have a lot of information on how the ECMO machine works and are able to give a lot of case studies. So those will be our main stakeholders. And then for Voice of the Customer, right now, we have not talked to too many people and have not been able to get in contact with our clinicians. So we're not exactly sure what they want, but based off of the clinical trials that we've seen and from the clinical emergence students, we know that a cannula tube, they want a cannula tube that better fits the veins and arteries of preterm babies between the weeks of 34 and 35.
And so for our disease state, some anatomy of premature babies for boys, they typically weigh 5 pounds, 8 ounces or less. And then for girls, somewhere around 5 pounds, 4.7 ounces or less. And then in terms of length of the girl, 45 centimeters or less, and 46 centimeters or less for boys. And so pathophysiology, we have the breathing problems that may occur, heart problems, brain problems, temperature control problems. For breathing, due to an immature respiratory system, The lungs could lack surfactant, which allows the lungs to expand. And because they won't be able to expand as they should, they could develop a respiratory distress syndrome. For the heart, preemies usually have patent ductus arteriosus, which is the opening between the aortic and pulmonary artery. And they also have a hypotension, which is just low blood pressure. And they have an underdeveloped immune system, which are common and have higher risk for infection due to this. And for clinical presentation, they're small in size. They have disproportionate head compared to their body, low body temperature, respiratory distress, and lack of reflexes. And some clinical outcomes, there are typically behavioral and psychological problems that could occur as they get to a older age. There are chronic health issues such as asthma, and some preemies may have impaired learning compared to their age group once they get older. And epidemiology, so some causes that could cause a premature birth are weight issues during pregnancy, whether it's being too thin or being overweight, conceiving through in vitro fertilization, and problems with the uterus, cervix, or placenta, and also having a previous premature birth. And for economic impact, the average cost for the first year of care of a premature baby ranges up to $49,000, and out-of-pocket cost averages for families are up to $1,987 for the first year.
So for our market segmentation, so there's a total of about 15,000 neonates born a year. And for the served market, so there's about 35,000 neonates who will require the ECMO machine. So our target market would be more so the pediatric surgeons and also the other people who are on the team, such as nurses and cardiovascular doctors, and also the hospitals. Well, basically the hospital's whole NICU department.
So some of the criteria we have for our ECMO machine would be it must conform to vessel and artery once placed within. So flexibility, must keep blood from clotting or coagulation from happening. Therefore, it needs to be have a coating within the tube. We wanted to have polyurethane material, must have side holes for drainage of blood, must not collapse once within the vein or artery, and must have a biocompatible coating within the tube. And some constraints, internal cannula diameter is important for us, which helps control blood flow resistance. Cannula size between 0.87 centimeters and 0.92 centimeters. For the VA machine, which is the venous arterial, we need the size of the tube to be within 6 to 8 FR, and for arterial size, 7 to 8 FR, and the cannula size should not exceed 3/4 of the vessel size.
And then just the science and engineering behind the concept. So basically, it's just the ECMO machine is utilized to bring oxygen into blood and then take out CO2. So our main focus, as we said, is the cannulation tube. And for that, they utilize the Poiseuille and Bernoulli equations to understand how approximate flow, as well as Reynolds number for the turbulence or laminar flow, and a number called by this guy named Montoya et al. And he created a M number, which basically estimates pressure and flow for the cannula tube. And these are references.
Questions, comments?
Yes, sir.
All right, thank you very much. Yes, thank you.
That was a nice presentation. I just curious the pronunciation of the word cannula.
Cannula
I
and
always thought it was
Cannula.
cannula.
It is
You were saying cannula.
We've been pronouncing it cannula for so long, but it is cannula. So.
Is it? I don't know. It just.
I have heard people based on like videos that I've watched with doctors explaining ECMO, they say cannula, but he just pronounced it cannula.
I love Cannula. I know it's right, but it sounds like.
Yeah, right for our foundation.
Other questions, suggestions? So for your criteria and your constraints, so for that first one, you say conform, are you talking about width or like direction?
So with that, I know for some of the cannula that we've researched, the polyurethane, it is temperature dependent, so when it's outside in air, it's more stiff, and then once it gets inside of the vessel or artery, it kind of becomes more malleable. So that's what we meant by conforming, being able to conform.
Okay, and then so once again, we'll have to figure out how to test this and quantify it. And why does it have to be polyurethane?
Just because that's based on research what we've seen the most. That's what works the most. But I'm trying to do more research to see if there's any other polymers that are better for this. But polyurethane is on the top as the most utilized material.
And so tell me a little bit about how you're gonna refine your actual market segment. Are you planning to capture all those 38,000 people, and is it like 1 unit per 38,000 units in the first year? Is that just in North Carolina, or 36,000?
This was just a total found from the ELSC, SO website, where they have all the stats for the actual ECMO machines. So more so needs to refine it based on the hospitals. So which hospitals have them, how many there are, maybe in each hospital, and then go from there.
And also looking at the weeks that we want.
Yeah.
And making sure that we have that certain amount of weeks.
And what ethical considerations or questions do you think this project brings up?
I would say sometimes it may bring up religion, more so because some people don't believe that they need extra help for someone to, I guess, survive. More so they feel like, I don't want to say God wants it, then he wants it, but something around that nature. And
probably like testing on babies, just because usually when they do run tests, in the case studies that I've seen, the babies that they utilize are ones close to death. So it's kind of like, are you trying to use somebody who's disposable just because, it's life or death, so why not? Or what do I do? So in that case, it would definitely be, I think a big part would be testing on babies who are near death, and is this ethical or not? Which apparently is chosen, so they've done it. See what that's ethical.
So for the tube, are you trying to like reduce the size of the tube, or, okay, so do you know the size that you want to get it down to? Did you say that?
so we're trying to exactly see we know the diameter of the vein, but it's more so if we reduce it to that size, is the blood flow still gonna be the same?
Because in one case study, there was a premature baby, and so they put him on ECMO as a last ditch effort, and they had him with a 8 French cannula. And once they tried to decannulate him, he wasn't reacting very well, so they had to keep him on. So they turned to a 5 French cannula, which was a lot smaller, but that still wasn't as adequate for flow, because the best flow comes from a shorter cannula with a larger diameter. So just trying to get a better size and shape, because shape really is dependent upon shape as well, just so to make sure that the blood runs through. So yeah, based on those, we're trying to just refine the cannula design.
Thank you. And last but definitely not least.
Not really.
We're ready whenever you are.
Yeah.
All right, yeah. All right, everybody, how y'all doing? My name is Simeon McKelvey,
I'm Tatiana Grant.
and this is the opening of the nasal airway. We don't have a team yet because Dr. Nicole said we can't have one. Yeah, you say you can't have one we want.
What's the one y'all want?
What is the one y'all want?
All right.
We'll ask at the end.
Okay, so originally our idea was to design a CPAP machine that was specifically marketed towards pediatric patients. We spent about a month trying to do this, and then we realized that our option was kind of untenable, and it wouldn't really recommend. So we had our meetings with our advisors, and then we had 3 different topics that we had to choose between. We ended up having to do a pros and cons list with the help of Dr. McCullough, and we narrowed it down to our final choice.
All right, so our final decision was to create a device for inferior turbinate out fracture, and we all get to watch one. It worked on her iPad, so theoretically. I don't know if it'll open on a different screen. Oh yeah, it opened on this screen. Yeah, it's crazy. It's very quick. All right, so he does some talking. Basically what they do, instead actually switches to a picture of this kid's face. They put a metal tool inside the nose, and there's a bony ridge on the outer side of your nose that they just break and push out, and that's the entire procedure. It takes very little time. Then he puts a tool in there just to show how much space he opened up. Poor kid. But anyway, so it's super medieval, so there's no like bells and whistles. It's just, we're just designing like an ice pick.
In your nose.
Yeah. And so what the turbinates actually do is they regulate airflow, and they warm and humidify the air as it goes into like your lungs. So like the best breathing that you do is actually through your nose, because these turbinates help, but they swell and lots of other problems, especially in children. So they need to be either pushed out of the way or grinded down, or there's all sorts of nasty stuff they do to them. But there are 3 turbinates in both sides of the nose, and we're just focusing on the bottom one because it is the largest and the one most likely to cause problems for breathing.
All right, this is our problem statement. I'll just read the whole thing since that's the problem statement. The tools that doctors use while completing inferior turbinate out fractures are not designed for turbinates, making them susceptible to many problems, such as damaging the mucosal lining. The tools they use now, it damages the mucosal lining if the doctor messes up. It can damage the turbinate, and you need your turbinates to breathe. And you got incomplete out fracture, which is like halfway breaking of a bone, and you don't want to halfway break a bone in your nose. And it causes major bleeding. And our need statement is within the hospital systems in North Carolina, about 20,000 inferior turbinate out fractures are done per year with no device specifically made for them. A device specifically made for the inferior turbinate out fractures can lead to less time under anesthesia, fewer follow-up appointments, and evenly fractured turbinates can lead to better breathing.
So for our stakeholder analysis, we actually reached out to 3 clinicians, Dr. Rose, who we were assigned and has been invaluable, Dr. Thomas Young at Marshall University, and Dr. Eric Mansfield at Cape Fear Valley Hospital. So we discussed the problem with them and found out how many out fractures they do, like what other things they do to reduce out fractures, because it's kind of a problem that there's a lot of solutions for, but none of them are great. So we're trying to make one that's a little better. And we settled on 3 hospital systems within North Carolina to make our quote unquote first year market sample. And then competing devices made or that are used today were invented in like the 1800s. So there's no there's no specialty device for this. Our doctor is using like a tonsil elevator or something that you would use for a throat surgery, and just breaking noses with it. So we feel pretty comfortable making this. For our disease state analysis, the actual disease or problem is inferior turbinate hypertrophy. It's just swelling of the turbinates. It's in the nose, obviously. The clinical presentation is altered sense of smell, dry mouth, basically problems breathing through your nose and anything that comes from that. Epidemiology, yeah, just when the mucosal lining swells, that causes problems for breathing because, it's a blockage. So you have to break the bone under that to push the whole thing out of the way. Economic impact is $712 per out fracture and $1664 per reduction, which is the other procedure that's done. And they use a variety of tools for that too. But that's what the hospital bills the insurance, as far as I know.
All right, so our market analysis for the first year. So there is 135,854 surgeons in the U.S. Of those, 9,600 of them are ENTs, and we are focusing on the ENTs for the first year in the UNC, Duke, and Wake Forest hospitals because they are teaching hospitals. And there's about 100 ENTs on their.
And so the regulation or the FDA regulation that most covers ours is class 1 ear, nose, and throat device because, like I said, we're basically just reinventing the ice pick. And these are our ice picks.
Yeah, this is a prior art search. I thought we needed that in there. These are elevators used now in out fractures. The herd elevator is what we see a lot because it's what Dr. Rose uses. And it's basically, I would say about 10 inches, maybe something around 10 inches long. But you see the top part where it's bent, that part is what it's used for. It's basically what it's made for. It's basically made for aneurysm and tonsillectomy, like Weston said.
And these are just.
And those are previous patents. The first one we found was in 1927. And we have the patent number here, and all the patents built on top of each other. So the last patent for an out fracture for turbinate was in 2009.
So our design constraints was that we needed our device to be sterilizable because it is being used in the operation room. We want the total price for manufacturing to be under $100 so that we actually make a profit from our device. We didn't need any specialty machinery to manufacture the device, and that the strength of our device was compatible to the ones that they're currently using. For our criteria, we want our device to be able to cut the turbinate, to be user-friendly so they don't have to go through special training to use it. Slip resistant because the current devices don't have anything on there and they actually slip out of your hands really easily. To be made of surgical steel, small enough to fit in the nose, and then 3 different sizes depend on the patients that they're going into because each patient has a different, well, when you're little or an adult, there's a different size turbinate.
Damn. Questions, comments, concerns? Was good. Suggestions? Max, you good?
Okay, my bad. I thought you were just playing behind me. So what percentage of the procedures done do actually damage the turbinates?
Well, the entire point is to damage the turbinates, but if it's a partial out fracture, which we don't have any solid numbers on that, then that causes problems because the whole turbinate isn't pushed out of the way, so the problem is still there, plus you have a broken bone in there, which is the point. But
and if they do mess up, that if they don't get a full out fracture, they get partial out fractures, the person has to go back into the hospital, and they usually most of the time after that. Reduction, yeah, they do a turbinate reduction, which it costs more and it takes longer. They have to get
Okay. So the purpose is to clear the airway?
Yeah, it's to help you breathe. So it's your turbinates, basically your turbinates swell, they block the airway for you breathing in your nose. And yeah, you want to be able to breathe because when you can't breathe at night when you're sleeping, you usually breathe through your nose. When you can't breathe through your nose, you wake up tired, less rested. You want to be able to focus.
How it happens? It's just a natural defect or?
Everyone just has swelling. It just depends. Some kids, they just since they have such small noses, they're just, it just happens, like allergies or whatever. Like anything that would cause sleep apnea or anything could be solved by this.
Allergies, and things like that usually cause one of the terminates.
Thank you, Dr. C, for joining us as well. Yeah, did you have any comments or questions?
Nothing specific, I would say, except for maybe one of the points here was not addressed about the ethical considerations or any. I mean, you said that the device should be sterilized, right?
Yeah.
Like, how are you going to?
How are we going to sterilize it, or?
I mean, not just sterilization, but how do you go about the ethical considerations?
I mean, so we use, we're gonna try to follow what main devices are used now, and most devices that they use, which are the outfractions, are sterilized inside the OR in a box that they use, in surgical box, where they send them to companies that sterilize different materials and come back to the hospital.
I mean, ideally, we're just making a surgical steel device, so it could be baked or whatever they do.
Thank you all. Oh, I'm sorry. Dr. C, do you have another point, question?
No, I'm good.
Okay. Thank you all as well for your presentation. Quickly, on the criteria side, next slide. Oh, I'm sorry, go back to constraints. So yeah, strength comparable. Do you have any ideas in terms of numbers or how strong this needs to be?
We actually have two devices, so we can use stuff at school, like they use to measure the device, the amount of force it needs to break and stuff like that they have here.
Is that heavily dependent on the surgeon, how much
force they use, sort of, because the device that we have now from the surgeon is not very.
It's not really thick.
Yeah, it's
and the terminates themselves are actually a really fragile bone, so it's not like there's a whole lot of force involved. And it is a surgical steel implement, so there's no concern that it's going to break or bend. You know, we're just trying to shoot for something that's around what they do.
Yeah, definitely want some, make some numbers on that for your testing. And you, just out of curiosity, do you know how much this will cost? So when you're talking about all the ENTs, the 3 hospital systems, or how much would that
cost? Yeah. How much it would cost to make the device, or
how much you would potentially bring in?
So we actually talked to Dr. Rose last time we were there, and he told us that he thinks they actually pay between $300 and $600
for each device.
Yeah.
So and it costs so about 150% income.
And so one per ENT?
Now they keep a stock, so 5 or 6 of these per ENT.
And since we're making different sizes, the reason we are making different sizes is for kids, children, and adults, so we can get the pediatric ENTs also have a set that you get adult ENTs. They use different
to buy more.
Good business plan. Any additional questions? All right, thank you very much.
Thank you.
Thank you all very much. All the best on your finals.
I see you started it.
Yeah,
I see you started it. That's what I like.
We need a team name on there though.
Team name unknown. For real.
Yeah, we do name.
Oh, we do. Yeah, we can use Terminators.
No, we can.
Huh?
We asked them.
I know why we can't use Terminators as a team name.
He said it has to be professional.
It's got to go on.
It's like PB&J. It's PB&J. It's the same. Terminators, terminates. You know. It's not like we terminate.
So are we going
to outrank them?
That's what we was asking me.
Do you want them?
Because it's the way we don't.
That's not actually.
I mean, if you want to.
I mean, do you want to come up here and hit me up? That's. I'm gonna be up here regardless because I can't do work at home, so I can only work at school. And what's tomorrow? Thursday?
Okay.
Thursday, tomorrow cool too, except I got a meeting at 2.
Can you just kind of try different
I got-
temperatures?
I got a vet appointment at 2. But
Okay, that's cool. Yeah.
I
I mean,
tried
shit,
to
honestly,
mention
skip
and then
transport.
try
I'm not doing it.
yeah, I wasn't planning on going if we're not doing the test. So.
Okay.
I'm gonna get him to explain.
But,
I guess it does, but.
Friday, yeah. This week, we can come Friday, like around 9 or something.
Okay.
What's a good time for you Friday?
Friday, we can do Friday at noon.
Noon.